Okay, we had a session for our 2 hours where we discussed about quantum memories, what is their requirement, and how do we implement them. We had briefly gone through, we are not got into the details within an hour or so. We will not be able to do that, but probably somebody is interested can just get into the details. Uh, okay, so what we will be doing today is we will see something more than what is quantum memories are. Okay, right? So just to recollect what we have done yesterday. Okay, so that we will have a continuity. Okay, so yesterday we started building knowledge on quantum memories, where we used classical memory as a build-up. Okay, right? So classical memories itself realized with various means, starting from transistors being in off and on mode, or for example, flash memories, hard disks, and magnetic disk based memories. Okay. When it comes to quantum memory, it is of something like some information is fed to quantum hardware, which stores the information. After some time, it retrieves. The fed information is in the form of quantum states. We can represent them on a block sphere, right, as a block vector. When I am doing this process of memory realization, I need to satisfy certain requirements. One such a thing is fidelity. We need to have long storage time, which is possible through having long coherence times. Okay, means coherence times in the sense the system should behave as per my requirement for a longer long time possible. On demand retrieval we expect, and we expect a very good efficiency of storage and retrieval, and we expect also storing lot of information, not just a very minimal, something like multi-mode capacity. We also expect compatibility with the flying qubits, which are photons. Means information has to store between, has to transfer between one node to other node in the form of qubits. So at the node level, it is stored as a stationary qubits. Okay. To transfer the stationary qubits from one node to other node, we need a flying qubits, which are photons. So the compatibility is required. And also the quantum memory should allow something very important is entanglement preservation, as entanglement is the very, very important recipe for having communication. Okay. So, and also this memory should allow you to realize lot and lot of scaling. Means you need to able to connect these nodes, quantum nodes, for a longer distance. Okay, right? So that we can have quantum channels or quantum networks. Okay, so that is what required when it comes to the requirement. Okay, so there is no trademark or something like we need to satisfy all of them with 100% accuracy. It's not that possible. We need, we can have some kind of a trade-off between some of the requirements, because having absolute perfect memories as of now, the technology wise, we have not reached that point yet. Okay, when it comes to various platforms, we gone through something called atomic ensembles, red earth ion doped crystals, single atom ions, okay, solid state defects like NV centers and silicon vacancies, and photonic memories are the ones are the flying qubits, and there is something called transforms, which are artificial atoms which mimics the naturally available atoms. So those things we use as a platform to realize various quantum memories. Okay. Among atomic ensembles, we checked about AIT based ensembles, rare earth ion doped crystals, where we see atomic frequency combs as a one of the way to realize memories. Okay. And when it comes to transmons, okay, it is LCR circuit, in fact, where inductor is replaced by superconducting materials, okay, and where it's not just a single superconductor, it's a sandwich of superconductor with an insulator. It is called Josephson junction that we discussed yesterday, okay, right? So, yeah, I'm sorry, still somebody is not able to hear. Please check. Uh, Dr. Madhu Mohanji, I am speaking. I hope others are hearing. I'm not on mute. You see, my screen is not on mute. Okay. Yeah. Santilji is confirming. If you are still not able to hear, please log out and log in again. I think it'll come back. Okay. Yeah. Thank you, others, for clarifying. Okay. So this is what we discussed yesterday. So we will be doing a quantum. Sorry, we did NV centers, photonic qubits, and ion trap. Okay, and the trade-offs should be you can have within a very short time one computation time, which means even for low coherence we can get a lot of operations on a given equipment or a given entity. It doesn't mean that is the best suited. For example, here you see ion traps, they may give a lot of operations, but when it comes to handling them, upscaling them may not be that easy. So that's why we have to go for something where we can connect them individually. Just see, that is why 80%, like 60 to 70% of the qubits were on based on LCR circuits, you see. Okay. So which are easy to connect some through radio frequency waves. They will connect them with the waveguides. Okay, that is what you see. A lot of coaxial cables in this chandelier IBM quantum hardware equipment picture, whatever we see everywhere on the net. Okay, so let's go further for today's topic. Okay, let me discard and open the next topic. Okay, just a minute. Okay, this is we saw repeaters. Okay, right. Yeah. Yes. So quantum repeaters and entanglement swapping. In a way, and repeater is a name or a nomenclature given to a process of entanglement swapping. Okay, right? Okay. Yeah. My yesterday notes, yes, it is not shared. I will ask the organizers to give the access to this QT-06 Canva. Okay, so Canvas. In that, I will share with my drive name. Okay, so since it was yesterday holiday, I did not request. Today, I will request the organizers to give me the access to Canvas. That is where you see all the materials. I will upload my both sessions, yesterday's and today's session material in it, and also hand notes in it. Don't worry. Please bear some time. Okay. Right. Okay. So here, like I said, entanglement swapping is a process. Okay, right? And repeaters, quantum repeaters is a nomenclature given to that. You just please understand in that way. Okay, fine. So let's go into details. What is this repeaters? Okay, fine. So as usual, the best way to understand a new topic, okay, let's say somebody has heard about it already, please wait, bear with us. Okay, for somebody who has not heard what is quantum repeaters earlier, for them, I would like to give some kind of a classical analog picture to understand what is there easily. Okay, here if you see, in classical communication, if I just have to send the information for a very, very longer distance, how do I do? I send using some classical channel like a say fiber or a wire or something. But thing is, as the signal transfers for a longer distance, what happens? It deteriorates as it consumes the energy, as it follows through, it deteriorates. Now the question is how to tackle that deterioration. So what I do, I use some kind of amplifiers. I use amplifiers to enhance the signal strength. Okay, and in that way, I'll communicate for a longer distance. So a repeater, what I am saying, is of such sort in quantum computing. Okay. If at all, if there is any repeater exist in classical communication, which is going to amplify the signals in the case of optical fibers. Right now, all the telecommunication is happening in optical fibers. Okay. In the form of light. So somewhere they might enhance the light signal strength by amplifying. Okay. But is that possible in the case of literally amplifying the signal strength in the case of quantum communication? Is that a question we can ask? Okay. So answer to that is very simple. We can't amplify the qubits. Okay. All right. We cannot recreate the qubits. Whatever it is there, I have to deal with them. I can't amplify their strength. So basically saying it is against the no cloning theorem. So I can't use the word amplification as such when it comes to quantum communication. Okay. So that is where I would be using some other means which is called quantum repeaters. Okay. What they usually do is very interesting. They extend the communication distance by, okay, to a longer distance. How it does? Very simple. It divides the given channel into shorter segments. Okay, for example, if I have a channel length, some length is there. If I have a node here, another node here. If I send a signal from node 1 to node 10, if I send, it will not able to reach because along the way it deteriorates. Probably what I'll do, now I will divide this entire channel into shorter segments. Let's say 1, 2, 3, 4, 5. Okay. Something like in between I'll create a segments where I use the quantum memories. How do I use the quantum memories? I'll put memories on both sides. Okay. Right. What I'm doing now, first of all, let me call node 1 and node 2, two memories, I entangle them. Okay. So I create an entanglement between 1 and 2. Then I will create entangle between 3 and 4, 5 and 6, 7 and 8, 9 and 10, 11 and, okay. The last one is 10, right? So let me call it as a 12. Okay. So 11 and 12. So between any consecutive, let's say 1 and 2 entanglement is created, 3 and 4 entanglement is created. Likewise, I create entanglement between each segments. Please remember there is nothing between 2 and 3 or 4 and 5, 6 and 7, 8 and 9, 10 and 11. Nothing is there. They are just sitting near to each other. That's all the memories. Okay. Now, this is what I have divided a given channel. Now, if you see between channel 1 to 2, in a class, between a channel 1 to 2, sending a information, intact is easy because it's a very small distance. What I'll do now, I do some very interesting stuff between 2 and 3. I do something between 2 and 3 means I take both 2 and 3. I do something, it's called Bell state measurement, BSM. We'll get into the details what is this BSM. If I do a BSM, interesting thing happens. 1 and 4 gets entangled. So earlier, only 1 and 2, 3 and 4 were individually entangled. The moment I do BSM, Bell state measurement on 2 and 3, 1 and 4 gets entangled. So my quantum channel now extended between 1 and 4. Okay. I'm not stopping at that point. Here at the right side, I do BSM between 10 and 11. Now the entanglement extends between 9 and 12. Okay. Like next thing what I'll do, you take 6 and 7, you do a BSM there. Okay. 6 and 7, if I do a BSM, 5 and 8 gets entangled. Okay. Now 5 and 8 gets entangled. Now if you see, now I have three segments of entanglement. One is 1 and 4, another one is 5 and 8, another one is 9 and 12. So I want to extend between 1 and 12. What I will do now, I will take 8 and 9, I will do the BSM. What happens now, the moment I do 8 and 9 BSM, the entanglement gets extended between 5 and 12. I'm not stopping at that point. I'll just do the entanglement BSM between 4 and 5. So altogether, I'll get connection between 1 and 12. So this is how I'm going to extend the entanglement. Okay. Bell state measurement I am going to do, which allows me to create the entanglement for a longer and longer distance. That is 1 and 12 nodes get entangled. Okay. Right. So that is I just explained here. Let's say I have node A, node B, node C. Okay. My objective is to create entanglement between A and C. Okay. So what I do, I am not able to do A and C directly. Okay. Okay. So for your understanding, what I'll do, I'll take a part of B and entangle with A, and part of B I'll entangle with C. I do a BSM on entire B, Bell state measurement, and in that way A and C gets entangled. Okay, right? So here the each node stores the entangled states until the neighboring segments get entangled or succeed in entanglement. Okay, so that is the purpose of quantum memory storage. Yesterday somebody was asking how quantum memory is going to help in communication. This is what they are actually used for. Okay, so you see now, whenever I do a Bell state measurement, what is happening is entanglement just swaps. Okay, between this channel and this channel, they get swapped in such a way the entire A and C got long distance channel gets entanglement. That is why it is known after the name of swapping, entanglement swapping. Okay, so that is what I said. Bell state measurement, okay, at intermediate nodes creates entanglement extension by step means. Okay, so final long distance entanglement, eventually two distance nodes becomes entangled even if they were never interacted in the first place. What they mean here, if A, B, C and D is there, okay, initially A and B are entangled, C and D are entangled with a BSM, okay, Bell state measurement, A and D gets entangled even though they have not individually interacted. Okay. So somebody was saying here, is theory this makes sense, but does this work practically, or is it super expensive to a certain such systems? Okay, right. So on theory, yes, you are right. What you are making point here is it makes sense at the theory level. Whether it is possible at the experimental level, that we will check today for sure. Okay, by checking at experimental level or the simulation level, you yourself can judge whether this is possible at experimental stage. Okay, we'll try to answer that question to whatever extent we can for today. Okay, right. So now here, entanglement swapping. Okay, so by definition, what it is this is, okay, right, uh, the process where two particles that have interacted become entangled via an intermediate measurement. It is an entanglement swapping. So, like I said, A and B already have an entanglement, and C and D already have an entanglement, or we create the entanglement between them. And B and C at intermediate node, when I make a Bell state measurement between them, BSM, A and D gets entangling, okay, is entanglement swapping. This is a building block of quantum repeaters and the quantum internet. So there are research works being conducted for realizing a quantum secure network. For that, the quantum repeaters are the key players, because we can't extend the communication channel for a longer distance without decay. But if through entanglement, you see what is entanglement by nature? It is a spooky action at distance. You mean what it is? It's a spooky action at distance. We never know why it is there. By nature, it is existing. Means without any delay, I do something with node A, I create some effect at node D instantaneously. So this is C. You see, absolute no delay. I can communicate between A and D without any delay using the entanglement. So if you are able to create an entanglement between A and D, you are through. You can do the communication without any resource consumption. But initially you might have consumed the resource to establish the entanglement, but later on you may not. Okay, right? And one more thing is, it is instantaneous. Simultaneously the communication results happen at the both places A and B when I do something with the A. Okay, fine. Okay, so the methodology, what is the methodology? So right now, for the methodology, what we'll do, we'll quickly use my hand notes and explain what is this methodology. Okay, so let me take my hand notes. Okay, fine. Okay, so we are trying to understand what is entanglement, quantum entanglement. I'll just say swapping. Okay, entanglement swapping. Okay, to understand this, first of all, we have to understand very few things. What are those things? Number one, let me tell you, we need to understand measurements. Measurement. Okay. So just to give me a minute, there is some noise coming here. Okay. So here we have to understand something called measurement. What is measurement? Yesterday we talked about. Measurement is something which measures the quantum state and gives us the insight about the quantum state. Okay. So, for example, a quantum state is there, alpha 0 plus beta 1. Okay. So, if I have to find what it is, see, since I have written on the paper, you know that it is made up of basis elements 0 and 1. Okay, it is constructed on a basis of 0 and 1. What is 0 and 1 basis? These are the eigenvectors of Z basis, Z matrix. Okay, right? We saw yesterday. What is Z matrix? Z matrix is 1, 0, 0, minus 1. It possesses eigenvalues plus and 1, minus 1. And eigenvectors, its eigenvectors are E1 is 1, 0, E2 is 0, 1, 1. Basically 0 ket and 1 ket. Whenever I multiply Z onto E1, I'll get E1. Whenever I multiply Z onto E2, I'll get minus of E2. This is the eigenvalue equation. Okay, so using this 0 ket and 1 ket are E1 and E2, I'll construct a measurement tool. What is the measurement tool? Yesterday we saw MZ0 is 0 outer product with 0, which is simply 1 0 1 0, which is going to be 1 0 0 0. Okay, so this is a measurement operator, and MZ1 is 1 outer cut with the 1, which is 0 1 0 1. You find out which is 0 0 1. This is a measurement operator. So these measurement operators would tell me what is the quantum state is made up of. Okay, so on paper, probing something, measuring something is simply action of that measurement matrix onto a quantum state. Basically, this will give you alpha 0 ket. Yesterday we saw that. You can cross check that. Okay. And when I make a measurement on something, I make several times. It's a probabilistic in nature. Like yesterday, somebody was pointing out, if there is so sensitive, when you make a measurement it's lost, right? Then how can you do repeated measurements? Okay, so yeah, let me change my voice speaker. Somebody was saying, okay, 1 minute. Can you hear me clear? Yes, sir, you are audible. Okay, thank you. Okay, yeah, okay. So when I make a measurement, it doesn't mean I'm only having one qubit. So it's a trick usually the when it comes to experiment, we take several kind of a qubits, several of them. Okay, so several of them I take, so I make several measurements of same kind of a qubits. When experimentalist is trying to prepare one qubit, he may not prepare one qubit. He will prepare a stream of qubits. Okay, right? A stream of photons of same kind. So through some pulses sent onto some hardware or some kind of a single electrons or something, they'll prepare and they'll make a repeated measurement. So when you even usually in statistics we do that. If I have to find what is the average, okay, like yesterday giving you example, let's say I have a thermometer. I'm not confident on the working of the thermometer. Sometimes it works, sometimes it doesn't work. In that case, what I do, I make a several measurements. I take the average of it. So I expect some value to come. So the same thing happens in the case of quantum mechanics. We expect some values, that is called expectation value of a measurement operator on a given quantum state, which is simply multiply the quantum state on the either side. We divide the entire thing with the normalized factor of quantum state if it is not normalized. If it is normalized, the denominator is simply equal to 1. So we will be getting, what we will be getting here? We will getting absolute alpha square. Okay, so this is the expectation value, that is will give me the probability, so which is simply p of 0. Similarly, P of 1 would be expectation value of MZ1. Okay, which is, you see, okay, what is MZ1? This one. If you want, you can say 0 kit and 1 kit. Okay, for your own comfortability. Okay, so this is going to give me the beta, absolute beta square, the probability. So the expectation value gives me a probability, and the state drops down. When I make a measurement, you see state drops down to 0 kit state. Here, when I make a measurement with the MZ1 on a quantum state drops to one of the 1 kit state. Okay, so this is what the measurement operators are. So on paper, it's easy to see. If some experimental qubit is given to you, to measure the qubit is made up of what? Is a 0 basis, 0 and 1 basis, or even X gate has its own eigenvectors and eigenvalues. What are they? Eigenvalues are for sure plus and 1, and its eigenvectors are u1, sorry, u0. Sorry, I'll take u plus and u minus. That is easier to understand. U plus is 1 by 1, 1. U minus is 1 by square root of 2, 1, 1 minus 1. Okay, so this is eigenvectors of x, and the bases are plus ket and minus ket are the basis elements. Quantum state can be even constructed, okay, constructed on these basis elements. The lambdas are eigenvalues, okay. So whenever I take a matrix, a square matrix, whenever I take a square matrix, let's say 2 by 2 square matrix, it is possess eigenvalues, which are represented using lambda, and it possesses eigenvectors which usually represented by some E or U. And the relation is A acting on the eigenvector is going to give me the scaled version of the eigenvalue. How it is scaled? With a lambda value. Okay. So this is the eigenvector equation. It is called eigenvalue or eigenvector equation. Okay. For any square matrix, this property exists. It is like lambda e's are some kind of a kits of this matrix A, and lambdas would tell me whether it's a first kid or a second kid. Okay, something of that information it gives. If you use that analogy, you would remember what is this eigenvalue equations are all about. Same, if you replace A with a Z, you are going to give lambda eigenvalues plus and minus 1 and E1, E2 as eigenvectors. If you replace A with a X, you would get plus ket and minus ket as eigenvectors. Okay, and eigenvalues are again plus and minus 1. Okay, so the basis of plus ket and minus ket are also one way of representing quantum state. Like yesterday we saw some dynamic, something which is moving in a two-dimensional surface could be represented by I cap and j cap, Cartesian coordinate system, Cartesian coordinate system. If something is moving in straight line, this is more suitable. If something is moving in curvilinear fashion, I go to polar coordinates to represent that. So this is called polar coordinates. Okay, right? I can give you a simple example. Somebody is moving in straight line in I, you represent using I and j. If something is moving in curved fashion, okay. So let's take a bicycle wheel. You put a bead. You just put a bead on one of the spoke. You rotate the wheel. What you see, the bead travels and makes a helical path, spiral. So see, even though it appears to move on a simple spoke, it is not. When it is rotated, it makes a helical path. Okay, right? So that helical path is actually represented easily by r and theta, not by polar Cartesian coordinate system. You can do that stubbornly. You can start using I and J to represent, but your entire description goes very, very complicated. It becomes so simple and straightforward in the case of polar coordinate system. Okay, so let me give you an example, simple equation here. You take r cos theta. That's all. It represents, I think. And one more equation is there, and you can check that. Okay. So coming back to the measurement here, if the quantum state is made up of, let's say, quantum state is made up of plus ket and minus ket. So whether it is made up of plus ket and minus ket, what I should use to measure, I should use a measurement of m. Okay, 1 minute. Mx plus ket, which is plus ket outer product plus ket. Mx minus is minus ket outer product minus. What is this one? This is one is 1 by square root of 2, 1, 1. 1 by square root of 2, 1, 1, which is going to give me 1 by 2, 1, 1, 1, 1. What about here? This will give me 1 by square root of 2, 1 minus 1, 1 by square root of 2, 1 minus 1. Okay, which is going to give me 1 by 2, 1 minus 1 minus 1, 1. Okay, so using these matrices, I can make a measurement mx plus or minus on a given quantum state. I am going to get whether it is A with the plus gate or B with the minus gate. I'm going to get. From there, I will find out whether the given state is made up of plus gate or minus gate, or whether it is made up of 0 gate and 1 gate. So let's say if the quantum state is given to you, okay, if the quantum state is given to you in a very, very complicated manner, what I will doing, I will have a measuring tools of mz0, mz1, mx plus, mx minus. So these are the 4 tools I have. I use 4 tools to measure the sign and get some output. Okay. Remember, when I make a measurement, the fate of the system changes from one form to other form. I can't guarantee the intactness of the system because you are fiddling with the system. Okay. So this is the measurement so far we saw for a 1 qubit system measurement. Okay. Right. So the first thing is 1 qubit measurement. Let me give you 1 qubit. Okay. There is something called 2 qubit measurement I can do. Okay. So 2 qubit measurement, which means I need to have a measurement tool which is related to 2 qubit system. Okay. So I can create any 2 qubit system. How do I create any 2 qubit system? Very simple. I take 1 qubit. Yesterday we did that. Okay. And take another qubit. Okay. And I put them together and make them interact. So interaction is represented by tensor product with the cross symbol. It's called tensor product. Okay, fine. So what is the tensor product? By the way, the column representation for this is alpha A, beta A. For this, alpha B, beta B. The tensor product means alpha A, beta A, tensor alpha B, beta B. So tensor product is very simple. You take alpha A multiplied to both the second terms. Take alpha beta A multiplied to alpha B, beta B. Okay. So what you are going to get is alpha A, alpha B, alpha A, beta B, beta A, alpha B, beta A, beta B. You see now, I started with the 1 qubit, I generated 2 qubit system. In short, I can write down easy this one for easy to remember as alpha 00, alpha 01, alpha 10, alpha 11. What is the corresponding basis elements? 00, 01, 10, 11. Okay. So this is a new basis for 2-qubit system. And remember, there is nothing new in it. It's just combining 2 dimensions. I created 4-dimension system. Okay. So 2 individual dimensions I combined. I created 4-dimension system. Now let me write down the combined system psi AB as alpha 0000, alpha 0110, alpha 10, sorry, 01, alpha 1010, alpha 1111. This is a system. Remember, it is just brought together. A and B brought together. There is nothing new happened with them. They are just about to interact. There is nothing else. Why I'm saying nothing else? Because if I want to separate them quantum mechanically, I can still do them separate. Why? I can just take a first one common here. I can take the second one. Sorry, sir. Yeah, 0. Yeah, sir. And then I can take a first one common here. I can, when I take a first one common, I am literally separating quantum mechanically. Remember, there are two things. One is quantum mechanical separability. One is physical separability. Physical separability doesn't mean quantum mechanical separability. Okay, right? So that is what the entanglement is all about. Even though things are separated spatially, they can still exist in the entanglement. Okay, so other way around is not there. If physically separable doesn't mean entanglement, right? Something which are no connected still, like entanglement not be ensured. So in order to have entanglement, you have to do some process that is already discussed to you people. Okay, what is that process is? So here I have a 2-qubit system which are about to interact. Somehow, please see, now I am making a statement. Somehow, if I am going to reduce the probability amplitudes of 0, 1 and 1, 0. Let's say somehow, okay, somehow if we reduce alpha 01 and alpha 10 to 0, if I reduce that, what happens? Alpha 00, alpha 11 now gets modified by themselves. That is how the quantum systems are all about. When I remove a presence of something at some location, means it is about to go somewhere else. It's like if I have, let's say a classroom is there, okay, right? If the chairs are there, let's say chairs, 100 chairs are there. If I go and ask the student, go and sit in a classroom, probably will come and sit in the front, or probably will go and sit in the back. Now, just to avoid students sitting at the back, what I'll do, I'll remove the back chairs. It doesn't mean student is not vacating the room. He will just come forward. Means his presence is still intact, but within the room it is there. So that is what I'm going to somehow remove the probability amplitudes of alpha 01 and 10. In that way, the new quantum state which is going to be formed, I will call it psi prime now, is going to have alpha 00 prime 00, beta, sorry, alpha 0, alpha 11 prime 11. This is a new state form. Remember, earlier also, the sum of all alphas, okay, is going to be, absolute square is going to be 1, right? Where I runs between 0 to 1, okay? Even now also, I need to have alpha 00 prime absolute square, alpha, okay, 1 minute, alpha 11 prime absolute square is equal to 1. This condition is must for any given quantum state. Okay. Now, if you carefully look at this new quantum state, if I specifically take the values alpha 0 0, alpha 0, 1 1 prime as 1 by square root of 2, what is the state I am getting here is a complete entangled state for alpha 0 0 prime, alpha 1 1 prime is equal to 1 by square root of 2. Okay, right? For this case, it is pure entangled state. What is this entangled state is? Even when I separate this physically, these two atoms A and B to a very longer distance, now it's a very interesting thing happens. Now let me individually write the probability amplitudes as 0, as 0, as 1, as 1. Okay, so this is what the state I have. Now, these two systems are quantum mechanically entangled. When I separate them for a longer distance, let's say A and B entangled, A is in one place, B is in one place. Now, as I know, when I make a measurement on one of them, the probability amplitude of the other state has to be reduced to 0. That is what the state happens, right? Okay. For example, let's take only system A. What is system A? This is system A. This is system B. When I make a measurement on the system A, let's say system A falls to one of the state. Which state? Let's say system A falls to 0 state. Means the one state has to be nullified or get rid of. How? The probability amplitude corresponding to that is reduced to 0. Okay, it is just reducing to 0 doesn't mean the same 1 by square root of 2 is also multiplying to 1. Just for convenience I just wrote separately, so I should remove it. Okay, you see now you see whenever the probability amplitude of 1 gets nullified to 0, which is also multiplying to 1, so the entire state get cancelled, which means the fate of B is also forced to fall to 0. So that is the entanglement. Two systems are separated even in space if they happen to have an entanglement between them established in the first place. In that case, make a measurement on the first one, going to push that to 0 state. The second one is also pushed to 0 state simultaneously in one go. So, making a measurement is having such an effect on them. Two systems. Okay, right? So, question is, how do I reduce a given psi AB to psi AB prime? Very simple. We have seen that. How? We just take one quantum resistor, act a Hadamard gate, okay, follow it up with the C naught gate. Okay, if the first one start register is in 0 0, at this point here what I'll have, I have a superposition state. What I'll have at this position, just a 0 state. What I'll be getting here, I'll be getting 0 0 plus 1 1 divided by square root of 2. You see, I just obtained psi AB prime by using a Hadamard gate followed by C naught gate. Okay, so if you want, I can write down what is the unitary operator for creating an entanglement on 0 0, giving you psi plus. Okay, is it the psi plus is represented? The Bell state psi plus is 0 0 plus 1 1 divided by square root of 2. This is a Bell state. Okay, now how it is done? Very simple. You have Hadamard and identity. This is the first part, and then you are following with you are following with C naught gate. Okay, so in the place of Hadamard, you see nothing is there on the second register. You can treat it as identity gate, and then you follow C naught gate between what? Between, okay, let me call this a Q0 and this is a Q1. So between Q0 to Q1, you have a C naught gate. So that is a unitary operator. acting on 0, 0 gives you this. Okay, so basically a unitary operator is an entanglement operator. Okay, right? And this is the entanglement process for you. You need to understand this. And interestingly, I can reverse this. I can reverse the entangling unitary operator. How do I reverse? I make it C naught first and I create a Hada mod later. So what I mean is C naught followed by Hada mod with identity. So this is actually called Bell State Measurement Tool, BSM. Okay, what is the role of this one is it will extend the entanglement for a longer distance. So the BSM which I was talking here is corresponding to this one. Okay, right? So we'll literally get the understanding of what is this BSM as we see the things in terms of a quantum circuit. Okay, right? So please, last line, please explain again. Okay, which line I mean? This one. Okay, so first I'll create the entanglement using Hadamard gate followed by CNOT gate. If I reverse that, if I reverse, what I mean by reverse is, let's say I have some register R, some register Q, R and Q. If I reverse C naught gate first and Hadamard gate later, that is action of Bell state measurement onto QR and QQ. Okay. Now the question is, earlier I said measurement is based on some measurement tools, right? And what is a measurement here? Okay, that is what I'm going to tell you. Bell state measurement tools. Okay, so what is this Bell state measurement tool says? You just please recollect every time what I told you earlier. Okay, right? What is that? For a Z basis, I have a measurement tools mz 0 comma 1. For x basis, I have a measurement tool which are mx plus minus. Similarly, a Bell state measurement tools also should have some measurement. Okay, right? Now for that, first of all, you should find out what are the Bell states. Okay, so there are 4 Bell states, the Bell pairs. You might have understood or gone through from first module to till now. What are the Bell pairs? Okay, just now I told you, if I have one register, first one is followed with Hada mod, second one followed with a C naught. If the first register is in 0 0, what do I get here? I get 0 0 plus 1 1 divided by square root of 2. This Bell pair or this entangled state, maximal entangled state, is represented by psi plus. Okay, if I get 0 0 minus 1 1 divided by square root of 2, if I get this, it is called psi minus. Now the question is, how do I get this? Very simple. How do I get is, if I take, I just initialization, if I just fiddle with this initialization, I will get that. So let me take, instead of 0, I'll just take the first register is 1. The first register is 1, second register is 0 as it is. If I do this, at this point you have 0 minus 1 divided by square root of 2, and everything else is the same. I'll get this output. Okay, just by control register, this is a control part, first register, I flip to 1, I'll get the psi minus, another Bell pair I'll got. Now not only that, I can also play with the target part also. What is this is, initial part is 0, this time the target is 1. Now you see at this point I have a positive superposition. Now the output is very interesting. Output would be 0 1 plus 1 0 divided by square root of 2. This is called psi plus entangled pair, okay, or bell pair. Now, what do you mean by this? Even when these two qubits are separated, let's say when I make a measurement on the first one, if the first one falls to 0, second one is forced to falls to 1. Okay, it's like opposite parity, opposite. Okay, it's like two guys interacted, they become enemies. When I hit the one guy, the other guy feels happy, something like a 0 state and 1 state. Okay, now if I have the first register is 1, second register is also 1. I'm sorry, this time what do I get? At this point I have 0 minus 1 due to the square root of 2. Output is 0 1 minus 1 0 divided by square root of 2. You see, this is psi minus. Okay, same circuit. See, same circuit, but only my initializations are different. Initial qubit states are different. When I have the initial states are different, I generated 4 different Bell states. So I am going to say there are 4 different Bell states, which are psi plus, psi minus, phi plus, phi minus. These are just like any basis elements for one qubit system. One qubit system, what are the bases? 0 and 1, plus and minus. Similarly, this is for two qubit system. For two qubit system, these are the 4 possible basis elements. Means the two qubits can be entangled in this way, or entangled in this way, or entangled in this way, or entangled in this way. 4 possible ways they can be entangled. Okay, so now the question is, let's say somebody given you a entangled system and asked you to please find out what kind of entanglement is that, whether it is entangled in psi plus manner or a psi minus or a phi plus or a phi minus. How do you know? You have to create a tool using these basic elements. Very simple. Earlier, to know given state is 0 or 1 or a plus or minus, I was using the basis elements of corresponding mx or mz. So now here I am going to create a Bell basis measurement tool. Bell basis measurement tools. Okay, what are these measurement tools? Earlier, having 0, I take outer product, I got mz0. Simple idea. I use the same thing here. I take a psi outer with the psi itself. I am going to get a measurement of, okay, what is this measurement? This is an entangled measurement of psi plus. Okay, and similarly, psi minus is going to give me entangled measurement tool with for psi minus. Okay, and phi plus is entanglement phi plus, phi minus entanglement phi minus. Okay, so using the same tools, so same basis elements, I constructed 4 measurement tools. You see now, I'm sorry, let's say entangle, 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 sorry, okay, entangle, okay, all of them. One is phi plus, one is psi minus, phi plus, phi minus. So 4 measuring tools I created. So if I take them, act on a given quantum state. Now I take m entangle psi plus, I act on psi AB. If I get the result in terms of some value multiplied by psi plus, if I get that, which means the given state is entangled with the psi plus manner. If I get something else, some non-conclusive result means you can say probably it is not entangled. Okay. If I get anything like psi minus, anything with the phi plus, okay, let me clearly write just to avoid confusion. Okay, anything, any scalar, this is scalar, remember, doesn't matter for me. It will give me the probability amplitude for sure. Its absolute square will give me what is the entanglement level, definitely. But the presence, whatever the state presence on the right side would tell me given state is entangled or not in the first place. Okay, right? Now the question is, given state is entangled or not, I need to use this measurement tool. Please remember now, very interesting. What is this measurement tool? It's just a measurement tool is a matrix multiplication. What is this matrix is made up of? Like I said now, the entanglement is created by Hadamard gate by C naught. Just reverse it. You just reverse, you would be getting the measurement tools. What measurement tools you'll get? mx plus, sorry, m for psi plus, m psi minus, m phi plus, m psi minus. That's all. These are created. These are the measurement tools now. Okay. So we will see this, how I am going to use them to extend the entanglement to a larger distance using the circuit. Okay. So before going into checking with the circuit, we'll take a quick 5 minutes break. It's now 4:02. We'll come back at 4:07. Okay. So just please stare at this. Okay. Maybe I'll project something. We can stare at that. Yeah, please. Okay. Just to keep staring at this figure and we'll discuss as we restart at 6:07 or 6:08. Okay. Sorry, 4:08. Welcome back, everyone. I'm not talking actually. I'm just started now. I hope you are hearing now, Dr. Koteshwari ji. Right. Yeah, great. So, just now I explained whether given qubits, two qubits are entangled or not. I need to check that. There are four possible ways I can entangle two qubit system, which are represented by four bell pairs. Using them, I can create a measurement tools. Acting a measurement tool on the given qubits, two qubit system, I can find out in what form it is entangled. Okay. There is something little more to this when it comes to quantum repeaters. Okay. Quantum repeaters is what you see here. There are four qubit system. You see carefully, please see here. Four qubit system I have. First qubit is initialized to 0. Second qubit is also initialized to 0. Third qubit is initialized to 0. Fourth qubit is initialized to 0. Forget about everything else. See things from section by section. Now you see, I want to create entanglement between first qubit and second qubit. The entanglement I want to create. What I do, we know that we'll have Hadamard gate on the first one, C0 gate on second to the first to second, which is going to create me the entangled state of psi plus. Remember, there is another way of representation for psi plus is, I'm sorry, it is also represented as beta 00. Okay, so that is what showed here. It is creating entanglement of psi plus between first and the second qubit. Similarly, the second qubit is initialized with the 00. Third qubit is initialized. Sorry, the first, second, third, and fourth. Fourth one is initialized with 00. I use the same kind of a circuit of Hadamard followed by C0, which is also creates an entanglement of psi plus between third and fourth qubit. Okay, so if we can say first one is A, second one is B, third one is C, fourth one is D. Now what I am doing, I am creating entanglement of A and B, entanglement of C and D. Okay, right? Now, as per my quantum repeater explanation earlier, I want to do a Bell state measurement between B and C, or Bell state measurement on B and C, so that the entanglement is extended between A and D. Okay? And you can ask a question to me straight away. Why are you going with so much hustle of Bell state measurement? Why can't I use just a Hadamard gate on the first qubit, C0 gate between first and the fourth qubit straight away? I will create a B00 entanglement between first and fourth qubit, right? You can say that. You are right. You are absolutely right. Please remember, what is a C0 gate operation? C0 gate operation is a correlation operation, which is a relative motion between first and fourth. Probably the length of having action between 0 to the fourth qubit involves a C0 gate. Probably by the time I take the information of nature of my control and go on act on the target as a C0 would require some information carriage from 1 to 4. That information carriage itself will take some time, or it might delay, or it might decay along the way. In that case, I cannot perfectly execute my C0 gate operation if the first and fourth qubit are separated to a longer distance. That is where I'm going to say I will just use my C naught only up to certain extent level only, certain distance only. In that case, I can't just use a conventional circuit to extend the entanglement to a longer distance. That is where quantum repeaters are coming into play. Okay, right? Now, what is a quantum repeater circuit? Very simple, like I said. I reverse C naught first and had a modulate. Okay, so that is the first part of the quantum repeater. Next part of the quantum repeater is make a measurement on the qubit, and whatever result, see, once you get the measurement, the output could be for a given qubit, the output could be 0 or 1. That's all. If it gets 0, I'll not do anything. I'll just keep quiet. If it gives me 1, state output 1, what I will do, depending the moment I get 1, means I do something, I need to do something. What is that something is, I act a Z gate operation on the first. What kind of a Z gate? It's a control Z. Means whenever control output is 1, then only the Z gate operation is done on the first qubit. Same thing I will do for the third qubit also. I'll make a measurement. If the output is 0 cat, I will keep quiet. If the output is 1, I'll make a X gate operation. So here, what is this? This is controlled Z operation. What is this? Control not operation. Okay. So my quantum repeater is C naught followed by Hadamard followed by control Z. Between there is a measurement. Okay. So if I have to write down my circuit operation, okay, quantum repeater circuit, repeater, okay, circuit. Let me do that. What is it? It is Hadamard followed by, okay, no, it is a C naught followed by Hadamard, okay, and then I have a measurement, okay, with the measurement onto the top if the, okay, and here again I have a measurement. This one, this result gives me the possibility of controlled X gate on the fourth qubit. This is on the first qubit, this is on the fourth qubit. Sorry, fourth means Q3. The indices is starting from 0. Okay, so this is the entire box of quantum repeater. Okay, so the quantum repeater circuit would look like this. You see, okay, whenever the output here is 1, only in that case there is a not Z operation is done. Whenever his output is 1, then only I'll get the X operation. Otherwise, no, nothing is need to be done. You just make a measurement and leave it. When you make a measurement and leave it, interestingly, what happens? Q0 and Q3 gets entangled. Okay, right? Yeah, let's see a question. Some questions here. Is this a linear entanglement used here? How to decide which type of entanglement has to be used? Okay, a very good question. There are 4 types of entanglement I have for you. I'm sorry. Okay. The question is which type of entanglement I have to use or you have to use. Very simple. You can pick any one of them. All 4 are maximally entangled types. Okay. Only they differ slightly from each other. Okay. Right? They are of the same level entanglement, maximally entangled. You can pick any one of them. Some people may choose the first one because it is easier to see, eye catching. Psi plus means 0, 0 plus 1, 1 divided by square root of 2. No complications there. No relative phase there. It is much easy to see. So probably people use that. Okay. It doesn't mean the other 3 are some kind of a problematic ones. Nothing like that. All are same. Okay, right. So the next question is, which simulation tool is used to design this circuit? Okay, so when you come back to the circuit, let me show you. Right. So you can do it with a Qiskit on you install it on your computer. You can execute this circuit, or you can go on IBM. Uh, you can go to their composer. Still, you can do this on a simulator. Okay, IBM composer. If you are wanted to do it on paper, you can do it on paper. I'll show you how to do it on paper ourselves. No. Now, what is the output? There is some output coming here. There is output coming here. So it's a 4 qubit system, right? It's a 4 qubit system, Q0, Q1, Q2, Q3. So there is a way of representing the statistics of 4 qubit system. How it is done? It is done kind of a histogram kind of a thing, where corresponding to each qubit, there is a horizontal and vertical scale I'll run. So Q0, Q1, Q2, Q3, Q0, Q1, Q2, Q3. Okay. Now let's say Q0 and Q3 are entangled with a probability amplitude of 1 by square root of 2 multiplying into 0, 0 and 1, 1. What do I do is I'll just make a grayscale for 0, 0 and 1, 1. And there is a possibility of representing even here, because Q0 is entangled to Q3, Q3 is entangled to Q1. So this is the representation on a histogram kind of a thing. If you are not able to understand, please ignore the representation. Straight away, you can go for understanding the expression, what comes out of the circuit. Okay, right? Fine. Yeah. So let me go part by part. Let's understand what is this circuit. Okay. So before going there, I'm just showing you how can I extend the entanglement from not between first to fourth. Let's say I want to entangle between first to eighth, first qubit to eighth qubit. You see now, okay, part by part you see. First I create entanglement between first two qubits, second two qubits, third qubits, fourth qubits. Okay. Now I want to create an entanglement extension from first to fourth. I'll do the Bell state measurement. Now I'll create the entanglement of Q0 and Q3. Okay. Now Bell state measurement between Q5 to Q6. I extend the entanglement from Q4 to Q7. Now I want to extend the entanglement from Q0 to Q7. Now I'll have a Bell state measurement on 3 and 4. That allows me the entangling extension between Q0 to Q7. The same circuit is repeated for additional another half of the circuit. Okay, so that is very simple. Now let's try to understand part by part what is happening here. Okay, so right, let me magnify for you so that you will understand better. Okay, now initially somebody is still saying we are not able to hear. Prahalad Rauji is saying. Others can just quickly let me know. Audible, yeah. Okay, thank you.
You are
Padma.
clearly audible, sir.
Yeah,
No
yeah,
problem. Maybe at your participant side there is a problem. So please check your connection.
yeah.
The lecture is going smoothly.
Yes, yes. Thank you, thank you, thank you. Yeah. So Yeah, Bell state measurement, sorry, Bell state representation. Is it a density matrix representation? Yeah. Yes, this is absolutely right. Okay. So far we did not bring in the density matrix concept yet. That's why I just jumped over. So in fact, this is a density matrix representation. Okay. So in the density matrix representation, you would be getting the density matrix. If you draw, you would be getting 1 0 0 1 0 0 0 0 0 0 0 1 0 0 0 for a 2 qubit entangled system. Wherever there is a 1, which is in fact multiplied by 1 by 2. So half, it means I do gray. If it is 1 completely, I'll do a dark. So it's a gray. So that is the density matrix representation for an entangling system. Yes, thank you, G. Somebody pointed out. Venkat, Dr. Venkat. Yeah. Okay. Now we were trying to understand exactly what happens at each level. Okay. Now you see, all the 4 qubits, I'm taking entangling or extending the entangling from 1 to 4. You see? Okay. Yeah. So for that, what I'm doing, initially I created all the 4 of them in 0 0 state. So I'm even saying quantum state at t0 means initial time. Initial time. All are there zeros. Now, next level. Next level is what? A Hanamat acting on the first. Okay. Identity acting on the second. Hadamard acting on the third. Identity acting on the fourth. Okay. Identity means nothing is there. I just say identity. So this is what I have. Okay. So literally, I just put in what is Hadamard in terms of matrix, which is going to act on a given state. Okay. When you act on the given state, I'm sorry, whenever Hadamard act on 0, what it gives me plus state. Whenever Hadamard act on plus 0, it gives me plus state. What is my output state? This is the output state. At some psi of t1. Later times. What is the time? This is the time. Okay. So my output after the first layer of quantum gates, this is the output, which is first qubit is in superposition, second qubit is in 0 state, third qubit in superposition, fourth qubit is in superposition. Okay. They are still individual. They may not be interacting. They are still existing as individual. Now I bring the correlation effect between them. Means some kind of an interaction I'm going to create. How I am going to create? Using the C0 gates. You see it? C0 between first to second and third to fourth. So that is, let me show you in the later. Okay. Now I have a C0 between, you see C0 gate is a 2 qubit gate. Okay. So C0 is acting between first to the second, third to the fourth. So obviously, whenever C0 is acted on a control, nothing happens to the control. So I have identity in the first quadrant, but the target gets flipped. I have a X gate in the third quadrant. That is what the C0 gate is. Similarly, C0 gate is there between third and fourth. I have a identity for the third place, flipping, that is X gate for the fourth place. Okay, right? So you see my output state before the T1 is plus 0 plus 0. Now C0 gate acts on first to second and third to fourth. Remember now, it is not that straightforward to understand easily from the circuit. You have to work on it. You have to work on the paper, or you can do the simulation using Qiskit. Okay, right? So if I do it, now what happens is entanglement is created between first and the second and third and the fourth. Okay, whenever entanglement is created between first and the second, I say B00 or beta 00 for first two qubits, beta 00 for the third and fourth qubit. Okay, if I represent them in a column representation, this is what they look like. Okay, so for your own convenience, let me show you how it would look like. Okay, so 00 Adamad followed by 0 C naught. Okay, so this is gives me 0 0 now. What is this? This is 1 by square root of 2 0 0 plus 1 1. Okay, this is the superposition state. Okay, it's a 2 qubit entangled superposition state. Okay, so by the way, what is the column representation for 0 0, which is this one? Nah? This is 1 0 1 0, which is 1 0 0 0. This is a column representation. What is a column representation for 1 1 kit? You can find out just like that. 0 1 0 1, which is 0 0 0 0 1. Now what is a B00 column representation? Which is very simple, 1 by square root of 2 multiplied by 1001. Okay, so we can write this as 1 by square root of 2 10001 transpose. Okay, so between Q0 and Q1 I have such thing. Between Q2 and Q3 again I have such thing, which means I have a such entanglement is there between first two and the later two. Means I have to have a resulting qubit. Let me call quantum state 1 2 3 4. 4 qubits, 4 qubits. Okay, which is beta 00 tensor beta 00. What is the representation? Representation is very simple. 1 by square root of 2 1001 tensor 1 by square root of 2 1000. Sorry, 1. Now what would be the overall? This is a 4 by 1. This is a 4 1 1 dimension. So what is the overall quantum state for 4 qubit system? 1 by 2. Now I'll have 16 elements. 16. Okay. So let me take a little bit lengthy. 16 elements. What is that size? Size would be 16 by 1. How it would look like? 1 0 0 1 0 0 0 0 0 0 0 0 1 0 0 1. This is what it would look like. Okay, so this is 1 by 2 1 0 0 1 0 0 0 0 0 0 0 0 1 0 0 1 transpose. So this is what I have in my presentation. See, there are 16 elements. Okay, only thing 1 by 2 put inside, I had put outside just for our own convenience. See, mid ones are 4 zeros. The last ones are 1 0 0 1. Okay, right? So I have created entanglement now between 1 and 2 and 2, 3 and 4. Now I want to do a Bell state measurement, the reverse. What is that reverse? First follows with the C naught. Okay, right? I'm sorry, just a minute. Yeah, yeah. So first I have a C naught followed by Hadamard gate. That is a Bell state measurement. So first of all, what is at T3? T3, I have something. Then for getting to T4, sorry, okay. Okay, T3 we need to discuss. We just finished a T2, and then we need to discuss what is output at T3. T3 is identity on the first qubit, identity on the fourth qubit, C naught between first and second qubit, second and third qubit. Okay, see identity on the first, identity on the fourth, C naught on second and third qubit. Now, second is a control, third is a target. That is what I have here. Second is a control, third is a target. Okay. Now, what happens in that case? You can literally find what is the overall matrix would look like, and then get the overall matrix, act on this 16-bit quantum state. Okay. Right? What is my C naught? What is my what is this as per the circuit? Okay, what is as per circuit? I need to have identity C naught followed by identity, which is 1001. Okay, right? And tensor 10. Okay, let me write C naught tensor 1001. Remember, it's not a matrix product, it's a tensor product. If I have a matrix product, this is not valid. Why it is not even dimensions mismatch? You see? So 2 by 2, I'm sorry, 2 by 2. Okay? So the output here would be, right? It will be a matrix of 16 by 16 dimensions. So I need to find out what is that exactly. You can easily find out by mathematics or doing a simulation. Here I am not doing it. It will take a lot of mathematical time. Okay. So once that C naught get acted, I'll get some psi 3 or psi at time T3. Okay. After that, I am acting a Hadamard gate only on the second qubit. Okay. That's a part of my Bell state measurement. So that is what I was showing here. Nothing on the first qubit, nothing on the second qubit, nothing on the third qubit, but only Hadamard on the second qubit. Okay. So what you see here is the I tensor I. Okay. The second order or 2-qubit identity matrix. Okay. Right. So after this, interestingly, you get something like this. Okay. Right. So you can cross check, and then what I'll do is I'll just check whether my output at the second qubit is 0 or 1. Okay. So for that, I use something called horizontal polarization gate. Means it's just like a MZ0. Okay. So it's basically tells me whether the whether the qubit which is coming out is in the horizontal or not. If it is in horizontal, I'll get a conclusive result. If I don't, means it is in the vertical plane. So let's say it gives me horizontal polarization. Both of them gives me horizontal polarization, which means as per my previous circuit, if you go back, okay, right, very early, if I get 0, I don't do anything. I don't do control Z. I don't do control not at the bottom. So that is what I am doing here. Okay, right? If I am getting a polarization horizontal means 0 output, 0 ket, 0 ket I am getting. I am going to keep quiet because whenever the mid qubits are falling into 0 means with my polarization horizontal measurement means whatever measurement I am forcing the mid ones to fall to 0 is in a way forces the first qubit and the fourth qubit falling into the entanglement. Okay, so that is by nature happens. Whatever the measurement I am doing here indirectly creates entanglement here, first and the fourth qubit. Okay, see, that is the role of making a measurement of pH here at the middle. So what is the output all the way at T5? T5, what is the output? This is the state which is being created. Okay. What is this state? Again, it has 16 outputs. Okay. So earlier, what was the entangled state we got? Okay. Right. Okay. So this is not entanglement between all the four states. This is entanglement between first two and the last two. Now I want to have entanglement between first and the last one. So what it says, as per my circuit, this is the state which is actually entanglement between first and the fourth one. Okay. So let me cross check. Okay. Okay. For your sake, we can spend some time on that. So what I'm saying is, okay, the first qubit is Q0, second qubit is Q1, third qubit is Q2, fourth qubit is Q3. Okay, what I'm saying is Q0 and Q3 are entangled. Okay, Q2 and Q3, sorry, Q1 and Q2 are in state 0. Okay, right? So how should I have represented this on paper? Okay, so on paper representing, unless I don't follow the circuit, it is not easy to do that. Okay, right? So yeah, it's not easy, so you have to follow the circuit. I'm sorry. Fine. So experimentally, how it is being realized, let me see. This is a circuit for you. Okay, if somebody has some doubt, you can let me know here. I can repeat if you want. Okay, you see, layer by layer. First, 4 qubits are taken. First two are entangled, second two are entangled. I do a Bell state measurement between second and third. Bell state measurement carries three operations. First is CNOT gate, followed by Hadamard gate, followed by measurement tools. The measurement tool is, let's say, MZ, I am taking MZ0. If the zero output is coming, I'll do nothing on the first and the fourth. If I'm getting 1 on the top, I'll do a Z operation on the top. If I get 1 on the bottom, I'll get a X operation on the bottom. Okay? What is a pH here? So pH is a polarization, horizontal polarization detecting gate. Okay. So what they are doing is, as per here, okay, if I have an electromagnetic wave going, you see, electromagnetic wave is electromagnetic wave is the energy which is traveling. So where horizontal, there is a electric field vector is oscillating in a vertical plane, magnetic field would be oscillating in a horizontal plane. So this is electromagnetic wave, see, where magnetic field vector is oscillating in the horizontal plane and it propagates along the way. Okay, this is electromagnetic wave. So now, okay, so electric field vector is the horizontal plane, means let's take horizontal. Horizontal plane is sorry, vertical plane is represented by V, horizontal is represented by H. Okay, so you can do other way around. A vertical is represented, okay, vertical is represented as a 1, H is represented as a 0. Okay, whether my quantum superposition state, sorry, quantum qubit coming out of the gates here, at this register, whether they are in the horizontal polarization or vertical polarization, I want to find out. If they are coming in a horizontal, I am representing them 0. They're coming in vertical, I'll represent them as 1. So the measurement tool pH is equivalent to a measurement operator MZ0. That is what. Okay, right? So yeah, it's not I should not have a direct representation, it is a pH. Okay, that is P stands for phase measurement, H stands for horizontal polarization. Okay, right. So I Hope you have understood that. Got it. Thank you. Okay, now in the experiments, how it is done. Okay, so in the experiments, how it is done is the quantum repeaters are extending the entanglement to a longer distance. Just remember, we need to have okay, we need to have some qubits. Okay, how are we going to get a qubits? We basically photons which are traveling. Okay, so here there is something called half wave plates with a phase of 22.5 degrees are taken. What this half wave plates are capable is they take, let's say I send a zero through a half wave plate, a polarization which is horizontal, let's say horizontal polarization wave I send through. What it does, it puts the horizontal polarization to a superposition state. What is a superposition state? Okay, let me represent. If Cartesian coordinate system is there, or let's say I take a system where my polarization of the vector, the photon is represented as the horizontal. It is in the initial state is horizontal. Now it goes through a half wave plate. What it does, it does rotate this horizontal polarization to diagonal polarization. What happens is polarization becomes like this. What it has happened, it is become a superposition of horizontal and vertical together. What kind of superposition? Equal superposition. So initial state is 0, which is equivalent to H. Going through half wave plate, it's like a crystal. Going through the crystal, light coming out is going to have both horizontal and vertical polarization, which is psi 1 psi prime is equal to h plus v divided by square root of 2. For you, I can write in terms of zeros and ones for understanding. So half wave plate is such a thing which creates a Hadamard gate operation. So I take a light with this vertical, one of the fixed polarization in one of the axis, horizontal or vertical. I send through half wave plate, I create a superposition state. Done. Okay, next thing is I want to create a effect of controlled NOT gate operation. Okay, so the controlled NOT gate operation is, okay, so here probably there are something called type 1 BBO crystal and quartz plates are used in such a way I will create some kind of a correlation between them. How? Very simple. I take first a part of the top. There is a beam splitter kind of a thing, BBO. It's like explained as barium borate crystal to produce type 1 down conversion. What is a down conversion is, if I send a photon of 100 joules to some crystal, it is divided into 50 joules of two photons. It's a energy is subdivided. So that is in a way it's called a splitting, a photonic down conversion. Okay, so I created many more, but only few things I could take. So some of them are blocked. There is a beam blocker. You just ignore that. Now I take one part from the top, one part from the bottom, and I used to mix them at another beam splitter. So they mix up, okay? So they create some kind of a control knot operation. So from the control knot operation, I'll take it up, okay? Now, this is a circuit would look like. Now, in this circuit, other than beam splitters and half wave plate, there is something called avalanche photodiode detectors also there. Okay, so that is actually represented here. APDs. Fine. So yeah, the Bell State okay beam splitter. So I am not getting into the exact details of the circuit. Okay, the experimental circuit. what experimental equipment is involved, that you can see through it. It's very difficult to less to connect each element of my quantum circuit to actual experimental circuit, because there are many more things are involved. This is just for pictorial interpretation I have taken. Okay, right? Okay, what is a OOJ? OOJ, where do I have OOJ? Let me see. 100 joules. Yeah. Sorry, it's 100 joules. Yes. So photonic down conversion. It's called photonic. Sorry, spontaneous down conversion, not photonic. It's a spontaneous down conversion. Okay. If somebody are still not convinced what is that is, very simple. I'll just take a three-level atomic system. 0, 1, 1. Okay. 0, 1, 2. Okay. So this is a three-level atomic system. There the chance there is electrons are there. I can excite directly these electrons to level 2. So let's say the level 1 and the level 0 and 1 are separated by energy of 100 joules. I'll send the photon of 100 joules. So electrons directly jump. Now they can't stay there forever. So electrons which are jumped to level 2, okay, now 1 and 2, 0 and 1 are equally separated. Let's say if I take it that way, now the electrons which just drop to 1 emit 50 joules, drop to just for a second, not even a second, for a moment it just stop and then emit another 50. So from one photon of 50 joule, I got two 50 joule photons. Okay, so using mode matching and other things, circuit QED, we can get this 100 joule photon split into 250 joule photon. Okay, so that is the method of beam splitting. Okay, right. So the circuit and experimental realization. Let's come back to the highlights. What is a quantum repeater? It is a simplified protocol that avoids classical disambiguation, less sensitive to synchronization, saving on a quantum computer, modular and scalable optical implementation, promising for fiber-based satellite quantum internet. You see, whatever we did so far can lead us to our secured quantum internet. So interestingly, you can do these simulations on the cloud with there are freely available simulators. Somebody was asking earlier something called a NetSquid. This is a cloud-based simulator from TU Delft from Netherlands. You can just create your own account and do the simulations. There is something called sequence simulator. Sequence. That simulator also you can use and create this quantum repeaters network and extend the network for a longer distance and you experiment. Okay, right? So now it's almost 5. Let's conclude the summary. A new entanglement swapping protocol simplifies the design. Experimental results confirm correctness and high fidelity. Please remember, it's not just theory, it is also experimentally proven. It reduces the cost and complexity of quantum repeater networks. Okay, and strong candidate for deployment in future quantum internet. The quantum repeaters are. Okay, right? So that is about it. So yeah, if you follow layer by layer quantum circuit interpretation, you would really understand and you would appreciate. Okay, so we have 5 minutes time. If there are any more questions, you can just ask. No questions? Okay. Once again, thank you very much for listening. Okay. All right. And yeah, the small things here, please remember in my notes, somewhere I write 1 by square root of 2 multiplying to a superposition state, which is actually bracket is missing. You need to be very careful while reading the whatever I'm writing. Okay, right? Fine. Yeah. Okay. So, yeah, there are questions. Let me see. Quantum measurements collapses to one state. Okay, that's a question. Explain the previous diagram. Okay, there is one question here. Okay, so quickly take what is a quantum measurement collapse. Okay, let's me take. So quantum measurement leading to collapse. Okay, so there are two ways I can see. One is classical analog, and literally see quantum version. Okay, yesterday we saw a classical analog. Today we'll see quantum version. What is quantum version? Let's say a quantum state I have alpha 0 plus. When I make a measurement, what is that I do? I take a measurement operator, I operate on it. Okay. So whenever it is in superposition state, means it is flipping between 0 and 1 continuously. It is oscillating between, the electron is oscillating between 0 and 1 continuously. So making a measurement means abruptly go and put some disturbance and see the oscillations by force. That way it will fall to one of them. By falling into one of them means what? The probability amplitude corresponding to other state is reduced to zero. Let's say beta is reduced to zero here. Means alpha becomes maximum, means the quantum state forced to falls to zero when I make a measurement. Okay, it's like a coin, a flipped coin classically is there. I just want to know what is it actually flipping, whether it's a 10 rupee coin, 5 rupee coin, or anything, 20 rupee coin. Nowadays it is there, right? So just to see what is that, I have to go and catch, or somebody goes and catch it. By the time they catch it, what happens? They're forcing it to fall to one of the state. That is what happens. Measurement forcing things to falls to one of the form. Earlier it is in a fuzzy state. Now I am clearing it fuzziness by catching it or forcing it to one of falling into one of them. Okay. So that is what measurement leading the system to fall into one of the form. Right? Okay then. And somebody was asking, please explain with the previous diagram. Okay. So I meant probably the previous diagram. There are many diagrams, huh? Okay, which diagram? I'm not sure which one you were asking. Probably the last one. Okay, probably this one, I guess. Yeah, probably this one. Okay, then. Initially, some output is taken. If I want to measure what form it is in, I'll measure and take the polarizations. Or, sorry, I'm sorry, it is the other way around. First, I'll take the lasers. Okay, and I use a half wave plate, put them into superposition. I use a quartz plates. Okay, I'll use through quartz plates. I can rotate whichever way I want. To have a control not operation, I use a BBO and some beam splitters, another laser, another beam I take, put them together. It's like controlled not operation. Based on the control, something should happen. So that is being done using that, and I'll take that output. Okay, and that output is in a way measured. Whatever is the measurement is led to the photodetectors. Okay, right? Fine. So let me remove the arrow mark here. So those photodetectors detect something and send to some time trigger. From there, I analyze. Okay, right? That is what the electrical, the actual experimental side would look like. But literally, what it allows me to do, it allows me to do entanglement extension. This is the entanglement extension through quantum repeaters. Okay, right? So somebody who had missed, I think, please, yeah, please go through the recording. It is available later, I think. Okay, then, thank you very much for listening and giving wonderful questions. I hope I made something constructive and useful for you people through this couple of sessions. I will also request the organizers, Sir Akshay sir, please give me that Canvas access today. I will upload both my notes to that drive.
Yes, sir. You can mail Mitrawal sir also, and he can upload on the drive or on the AI Academy,
Yeah,
AICT Academy mail ID from which you are getting
correct. But
or
can you
Zoom
please
link
send me the
link.
link again? Link again.
Yes, 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 yes,
Please
yes.
send me
I
the
will
link
send.
again. I'll upload it. Yeah.
Yes, sir. No problem. That will be shared with the participants. And as sir already said, the all lectures are available on the YouTube, so you can go through these YouTubes once again, so that the all lectures will be refreshed up, so that you are able to take the quiz also. It will be beneficial to the quiz. And thank you, Dr. Ashwath, for taking your time for 2 days. Even on Sunday, you are also available for us. So we all are thankful, our coordination committee and all the participants. The lecture you have already taken is interacting. That's why there is too much queries. That is not seen in other lectures. Because when participants are interacting, that means the lecture is going to be interested with them. So thank you very much again, once again, and thank you all the participants. We will meet again tomorrow from 3 to 5. Mm, Sir, your mail ID. Actually, yes. I can share on the canvas also if you want, sir, mail ID, or directly, sir, can
I'll
want
type.
to share.
I will type, sir. I will type here. Ashwath at triple ITDWT dot AC dot in. Yeah.
It means the participants are interested even after lecture also to contact with you.
Thank you. Thank you. Yeah, I sent my email ID. Yeah. Okay.
For further queries, if sir have time, then he
Yeah,
can
I'll
address.
definitely get back. So yeah, yes, I'll share the notes. Yes. Okay, sir.
Okay, thank you, sir. Thank you.